Hello everyone, my name is Gaurav Arora and I welcome you to the fourth lecture of Spatial Statistics and Spatial Econometrics. So till now we have covered, we have seen a lot of spatial data and their applications in different domains, which gives us an understanding of how widely applicable these data are as of today. We have looked at the data generating process, which is specifically the remote sensing technology, the satellite sensor technology, and so on and so forth. We also looked at the GIS, which is a computer software and hardware system to store, manipulate, analyze, visualize spatial data. Then in the last lecture, we looked at what are called as the spatial data structures. These are, in particular, the raster data structure and the vector data structure, and we talked about how, these are different and how their applications differ from problem to problem, right? So today, we will move, more formally to the statistics part and start departing from the data, part of this course. So today we'll formally talk about spatial statistics, its scope and purpose. So let's get started. So the first most primary basic component of spatial data modeling are spatial locations. So if you have any kind of spatial data, you need to formally articulate what the locations are, right? So here what I have is a set of discrete locations S1 to Sn, right? So data in a space, in a given space or domain are located at locations S1, S2, S3, S4, S5, S6, and so on till Sn, right? Each location will have a coordinate system. For example, if this is a two-dimensional domain, then S1 will have a x1 coordinate and y1 coordinate, also known as latitudes and longitudes, in remote sensing science, right? And then at these locations, we actually observe spatial data. So these spatial data are then articulated as value z observed at location S1, value z observed at location S2, and so on, value z observed at location Sn. So the uniqueness or the distinctness of spatial data that is observed at different locations is derived from the virtue of the location itself. That's the basic component of spatial data analysis, right? And data are assumed to be random. So at each location, what we assume is that you could observe a range of values of z, and these range can be characterized by a probability distribution function, right? This is something we will cover in more detail later today or in the next lecture. But the idea is that z Si is itself a random variable, right? And when we characterize a random variable, we usually will, we will use a probability distribution function, which is to say there is a PDF f linked to location Si, which tells me what is the range of values that this random variable z can take at location Si. Right? So there will be a probability distribution at Si, which will determine the values that ZSI can take that we mark on the x-axis. Again, we will look at these things with much more detail going forward. Okay, and Si is one of the locations that are there in my two-dimensional space that I am concerned about. Further, and very importantly, for this particular course, we will take locations to be deterministic or fixed. So we do not consider any kind of uncertainty in the location itself. So if we observe, let's say for example, groundwater, levels at location S1, we say that groundwater levels by itself is a random variable, but the location has no uncertainty, right? It couldn't be S1 plus minus delta, right? It is indeed exactly precisely at S1 that we observe Z of S1. Z by itself at S1 is random. So groundwater level is random, but the location is fixed, right? This is an assumption, right? This is an assumption. You can have uncertainty in the positioning of data as well, but that we deem out of scope for this particular course, right? So we'll take locations as fixed, and we will take data, that is the observations, the realizations at each location, to be random variables. So this is something we have talked about at length. So one component of spatial data is measurement, storage, retrieval through GIS system. GIS is a collection of computer software tools that facilitate georeferencing of spatial data. We understand these things now. It also sort of facilitates integration of spatial entities with qualitative and quantitative information, and then all of that can be managed in one environment. It mobilizes computational sciences, specifically computational geometry, spatial languages and user interfaces, something that we will look at. All of these components we will study, but this is about management, storage, and so on. We are now going to be more concerned about the statistical characterization of these data, right? So let's move to that. But when we talk about spatial data, this is an important component. We have spent quite a bit of time on this, and now we are moving to the statistical understanding of these data. So in order to characterizing spatial data, right? So in characterizing spatial data, the concept of distance between two locations is fundamental, right? So we cannot really model spatial data unless we are able to measure distance between any two given pair of locations where we observe data, right? So here what we do is we give you a most general form of two locations denoted as U and V, right? And these are vectors, right? So and these are vectors in d-dimensional space, right? So these are vectors in d-dimensional real space, right? We can always, whenever we look at this generalization to d-dimensional space, we can always learn or figure it out further by putting d equals 2, that is a two-dimensional space, something we understand very well, right? So how do I visualize U and V in two-dimensional space? So now my vector U, which is bold in the typed out text, I'm just using a top arrow to denote that it is a vector. It will have two components, U1, U2, which will be in R2. So U1, U2 are nothing but XY coordinates or latitudes and longitudes of the data. And now location V is given by V1 and V2. Again, these are just XY coordinates at this second location, which will lie on the second two-dimensional real space, right? And in this two-dimensional real space where you have X and Y, right, we can have vector U given by U1 comma U2 from the origin. This is my vector U, and vector V could be given by this joining the origin to a point which is characterized by the coordinates V1 comma V2. Okay. Given these, the question is, how do I figure out the distance between these two spatial locations, right? Unless we are able to measure this distance, we'll not be able to characterize what is the dependence, how dependent are these two, the observations that we see or the random variables that we see at these two locations are. So to be able to characterize that, we need to characterize distance. The most popular three metrics for doing that is called as the Manhattan distance, the Euclidean distance, and the great arc distance, right? I'm sure some of you must have heard of these earlier. So the Manhattan distance is nothing but a summation of the absolute difference of each coordinate values at these locations. So for our example, the Manhattan distance u minus v, Manhattan distance will be given as summation k equals 1 to 2 and absolute difference between uk minus vk, right, which is equal to nothing but absolute difference between u1 and v1 plus the absolute difference between u2 and v2. Okay. Similarly, the Euclidean distance, which is also known as the shortest path, right, that is given as which is called as the L2 norm, can be written as following in the two-dimensional space: k equals 1 to 2, uk minus vk the whole squared, which is nothing but u1 minus v1 the whole squared plus u2 minus v2 the whole squared. Okay. Now let's move forward and visualize what these distances mean. So first of all, I'm giving them these characterization L1 norm and L2 norm, and I want to sort of now formally define what a norm really is. A norm reference refers to the length of vectors between 2 points in space. So let's go back to our characterization. So we had points u and v in front of your screens, and the distance between them is the length of vector between these 2 points. So the norm is a formal quantitative measure of the distance between these 2 points. The Manhattan distance is the distance traveled between point coordinates u and v in a way that it resembles how a taxi cab would drive between city blocks to arrive at its destination, starting from point u to point v. So let's go back and visualize this. So on your screens on the left, you have a picture which shows you, a red line, a blue line, and a yellow line, all of which are alternative routes that a taxi cab would take between city blocks to arrive from point u to point v. Okay, so that is what Manhattan distance really is able to calculate. The second type of measure for distance between any two given points in space is called as the Euclidean distance, and this is indeed the shortest path between the points u and v. So again, go back to the picture. The green line is what we call as the Euclidean distance, right? So this is the L2 norm, and the green, blue, and yellow lines, as I said earlier, are called L1 norm, or they are termed as the Manhattan distance. The Manhattan distance. Okay. The third kind is called as the great arc distance, which basically takes into account the fact that the shape of Earth is a sphere. So if I'm moving from point u to v, I would have to move on a arc rather than a straight line between u and v. So this distinction gives us yet another alternative measure of distance between 2 points in space, which is called as the great arc distance. Okay. So these are primitive distance metrics. So we have more sophisticated distance metrics. I mean, you can imagine in India, the taxi cab characterization between city blocks would not really work, right? So you will have more sort of complicated, sophisticated pathways that a taxi cab would take if they are following let's say a Google Maps route, right? So road miles that they cover, or road kilometers that they would cover, provides us yet another metric of distance between 2 points u and v in space. Another method is called as the travel cost method. So now travel cost accounts for not only distances but also things like time and convenience. So you can have issues like traffic congestion, right? All those concepts can also be sort of brought into defining distance between two locations. So that these are more sophisticated measures. But the question is, what is the utility of distance metrics, right? So the utility really is to be able to model or identify clustering between different pairs of points or locations in space where we are able to observe data. Here, usually regions that are closer together might be clustered together, right? And that sort of gives us a point forward in terms of understanding or characterizing spatial dependence in data. Let's look at this example of the real estate market of Delhi. So the map that you see is a map of average circle rates, which is rupees in meter squares, where you have different districts in the National Capital Territory of Delhi. The light yellow colors are referring to low average circle rates in a given district. That is, land is relatively inexpensive in those areas. And the darker circles, darker sort of blocks or polygons are the ones where the land is priced at an expensive rate, right? So what you see here is that, let's say if we consider District 1, District 2, and District 3 on this map, the distance between District 1 and 2 would be likely sort of will be calculated between the center of mass of these districts respectively, right? So the center of mass of District 1 versus center of mass of District 2 will have certain distance length. It can be calculated using the Manhattan length, the Euclidean length, or Euclidean distance, or the great arc distance, or even more sophisticated measures, right? Similarly, 2 and 3 also will have a distance calculated between them, between their respective center of masses, right? Now, what we see here on this picture, when we look at it, it seems like the distance between 1 and 2 is quite similar to distance between 2 and 3. However, 2 and 3 encounter a natural barrier in terms of the river Yamuna, right? So this natural barrier will require us to have a more sophisticated distance metric than a direct calculation of a Euclidean distance between points 2 and 3, right? So this natural barrier, what it can do is it can cause reversal of trends in terms of the real estate values. Something like that we see if we look at the map of Delhi. If we come from west to east, when we come from west to east, we see that the real estate prices are rising. But as soon as we hit the natural barrier and we go on the other side, the prices are drastically lower, right? That sort of reversal can come from a natural barrier, which is also a geographic entity, which we want to sort of try and model, through the tools that we learn in this course. So what I'm trying to really say is that distance between two entities is a fundamental metric of how we can study spatial data, dependence between them, things like clustering and so on and so forth. And how we measure distance can be highly sophisticated, rather should be sophisticated enough, so that we can actually model the real world observations that we see. An example of which here is that the natural barrier can actually cause a reversal of trends in terms of the real estate values in New Delhi. This is a real world data providing us a sort of a motivation to think about distance very carefully when we work with these data. Okay, so let's come to spatial data modeling. So the earliest attempt one can, that one can think of in terms of spatial models was done by a student in 1907 who modeled the distribution of particles throughout a liquid. He divided 1 square millimeter area of volume, 1 square millimeter area, sorry, into 400 squares and counted number of particles in each square. So he basically took a flask of liquid, he took a cross section of 1 square millimeter, 1 millimeter squared, he divided it into grids, 400 cells of equal sizes, and started counting number of particles in each square. So what you have is a count variable. So you have a count of number of particles in square 1, in square 2, square 3, square 4, and so on, and in 400 squares. So when he modeled it, right, when he modeled it, he had to be careful about where is the square that he is counting the number of particles in. Are those squares on the edges of this 1 square millimeter cube, area domain that he's counting his particles in, or is that in somewhere in the middle? Does he see higher density of count or higher counts in the middle, or he sees higher counts on the edges, right? So you can have higher clustering of points in the middle or higher clustering of points on the edges or vice versa, right? So all of a sudden, this exercise that was done in 1907 has a documented, characterization of space, although not as sophisticated in terms of mathematical and statistical tools as we do today, but people were trying to already understand these methods at that time. The other area where spatial models have been there for a while now is agricultural field experiments. So agricultural field experiments are done to estimate yields, that is output per unit area on agricultural lands. And there you can imagine that you can have two farms together growing, let's say, wheat. The kind of output per unit area that you're going to expect to observe on these farms is going to be quite similar, right? Because they are side by side. What would change? They will experience similar rainfall, similar sunlight. They will have similar soils. The farmers are likely to probably come from similar backgrounds. I mean, it is possible that the one farmer is richer than the other. Let's assume that they have similar social, economic background, cultural influences, and so on and so forth, right? It's quite possible that plots that are located nearer in space will have similar yield values than plots that are located farther away, right? So researchers have been actively choosing plot dimensions over which they conduct these experiments strategically in order to account for spatial dependence or spatial correlation in a way that they have distinct understanding when they move from plot 1 to plot 2. If these plots are large enough, it's likely that you are going to have a distinct understanding of yield levels when you move from plot 1 to plot 2. Otherwise, if you don't do that, you can have 100 plots highly correlated with each other. You are really not learning much about what's happening on average in a region, right? Then there are methods like nearest neighbor methods that account for spatial dependence. We will talk about those in detail later. I don't want to, you can take a look at this. The only thing that I want to say is that the value that is observed at location I depends on what's happening at location Ni, where Ni is simply a set of neighbors of I, right? There are other statistical techniques like block bootstrap methods to neutralize spatial correlation in data. These are things that we will learn later, but I just wanted to put it out there for your notes, okay? So let's come to a general spatial model. A general spatial model, first of all, has a generic space location in d-dimensional Euclidean space, okay? So when we say this, we have said quite a bit. First of all, we have said that location will be indexed by S, right? S will be part of a d-dimensional real space. Whenever we see this generalized D, what we have learned till now, we just set D equals 2 and we start to develop our concepts from there. So we can have a generic location parameter S, which identifies different points in a two-dimensional space with coordinates x and y in R2 space, right? And what we are also saying is that we are going to work with a Euclidean space. So now when we specify or we declare a Euclidean space, what we are also declaring is our method of measuring distance between 2 points, right? So we have said quite a bit in that one sentence, right? Now suppose the datum, which is the data point, Z in location or at location S is a random quantity. Now we have seen what we mean by a random quantity is that Z of S is going to be distributed by a probability distribution function which is specific to that location S and allows us to draw different realizations of Z, right? and S can vary over the index set or domain D in the D-dimensional space. So again, I'm going to set D equals 2. I am simply working with a given specific domain D. So of course, the real two-dimensional real space is infinitum of the x coordinate and the y coordinate jointly put together as orthogonal axes, right? So I have x which goes from minus infinity to plus infinity. There is y axis, it goes from minus infinity to plus infinity. I define a domain D which is my area of analysis, all right? So I'm going to define a domain D in this area. Of course, it doesn't have to be a rectangle, it doesn't have to be a square, it can be any regular polygon that you can imagine. So I can also sort of draw a more complicated domain D for your understanding, and S is only allowed to vary in this D. Okay, so at a time we are going to work with a given domain in this D-dimensional real space. To understand concepts, again, we are setting D equals 2. Then a multivariate spatial model. A multivariate spatial model. So we have used the term multivariate. So we are going to work with multiple variables, and the variables that we have are the random variables. So multiple random variables are going to be denoted in a spatial model as following. You are going to have Z as a vector, which is in bold, given with the index location S, which is itself also a vector, because it can be a two-dimensional vector, a three-dimensional vector, depending on S being in what type of a D-dimensional space, right? And S must belong to D. So we are going to restrict our analysis or our model of the data, characterization of the data to D, to this set D. Okay. So what we are saying is that this Z capital, bold S, bold, basically which are vectors, what we are saying is that these are a multivariate vector. So you have multiple variables. So you have Z at location S1, you have Z at location S2, so on Z at location Sn. Okay. And each S itself is a vector, which basically means that this S is x comma y, x1 comma y1, S2 is x2 comma y2, and keep going, and Sn is xn comma yn. Such that S, that is S1, S2, keep going, Sn must lie in the domain of interest, right? So the analyst at least gets the choice to work with the domain that they want to work for, right? So you can't really be working for an indefinite space to begin with, right? I mean, you need to be able to fix a domain for which you are going to observe data, right? You're not going to be able to observe data in a real space which is unbounded, right? That kind of analysis is untractable, so we do not do that. We fix D and we move forward from there. And so these are all random variables, and a realization in space is given by small z, right? From capital to small z and at every location S. So we only get to observe one entity, one realization for the entire random variable. We will formally look at what this really means, but a realization in space is given by small z, right? And we have said that D is going to be, we are going to assume that D is fixed. It could be random, but that is out of scope for this particular course, right? Okay, so what are the different types of data that would follow that given model? The most popular kind is called as the geostatistical data. Here, D contains a D-dimensional rectangle of fixed positive volume. So what we are looking at is a rectangle. This would be a rectangle in D equals 2, and in D equals 3, it's going to be a three-dimensional, cube, could be a D-dimensional or three-dimensional, fixed positive volume domain that we are working with. And when a spatial process that varies continuously is observed only at few points in space, that is what is deemed to be a geostatistical data set. An example that I'm giving here is mineral concentrations at different locations in space. So the idea is that on land, when I'm trying to extract, for example, I'm trying to extract coal, or on sea, I'm trying to sort of search for oil, the point is that oil exists almost everywhere in this domain D, right? So oil will exist at all locations in D, right? But I can only monitor or observe the whether or not I can find oil or not, or how much is the quantity, what's the level or depth where I can extract oil from, at only certain search locations, right? Practically I can only probe certain locations in D, right? Although I am probing only certain locations, there are possible observations at every location that is possible in D. So you have infinitely many points in D that you can actually find the quantity or quality of oil that is available, right? So that is what is called as a geostatistical data set. I've given a wide range of applications that come with geostatistical data set. This is the most popular kind, and we will in most of this course we will be looking at this type of a data set. So again, we have talked about spatial heterogeneity, spatial dependence, large scale spatial trends, small scale spatial correlation, spatial dependence. Those types of understandings will start to directly apply to these data. The second kind, so here are some examples of geostatistical data. One of the most prominent example is groundwater. Here is an example of groundwater quality, that is fluoride contamination. The idea is that, look, you will have groundwater everywhere. The question is, where can you really observe it? Wherever you dig a well, you'll be able to observe what's happening there in terms of quantity and quality. But that doesn't mean that wherever I have not dug, there is no groundwater. The groundwater is available at continuum at the entire domain D of interest. Here in this left picture, the domain of interest is the entire conterminous region of India, right, as a country. On the left, the region of interest sort of is, let's say, it's mostly states ranging from Punjab, Delhi, Haryana, Rajasthan and Gujarat, and then there are some states in south. So you have a more restrictive region of interest that you're looking at on the right hand side. So you can have both possibilities with these data. The second type of spatial data are called as the lattice data. Again, here D is a fixed, regular or irregular collection of countably many points of the D-dimensional real space. So here I do not have entities moving continuously throughout the space. I will have fixed, given, regular or irregularly spaced points where I can observe data. A very good example of this is states in India, right? So if I'm observing GDP levels at state, for different states in India, I can only move through the centers of mass of different states in India, right? I cannot really tell you what's happening within each state if I only have observation at the level of state GDP for India in 2021. Right? So there, if you have such administrative boundaries, country boundaries, district boundaries, taluk boundaries, and so on and so forth, some kind of an aggregated unit level data, that is known as the lattice data. And a very natural example is in front of you is infant mortality rate for a region in China in 2000. What you see here are irregularly spaced, irregularly shaped, but fixed and given administrative units that are districts in this region where you can observe infant mortality rate, right? Within a given fixed, region of observation, you do not observe different levels of infant mortality. You have one level which is given at its center of mass. So you basically have discrete centers of mass where you can observe data, right? So that is called as, this type of data set is called as the lattice data, right? So this is something we have talked about. Now we have integrating groundwater management at district level, right? So there are many applications as such. The real estate data that we saw for the National Capital Territory of Delhi was a lattice data, right? So we have seen this and we have used this example multiple times throughout this course. The third kind of data is called as the point pattern data. When a spatial process is observed at a set of locations and the locations themselves are of interest, are of interest in the sense are a random variable of interest. So if the location themselves are a random variables of interest, then those spatial processes are modeled as point patterns. The easiest way to visualize a two-dimensional point pattern is a map of locations, which is simply a scatter plot, but with the provision that axes are equally spaced, right? Here, this domain D, the capital D domain, with which we are working, is basically a convex hull of points which are random variables of interest in space, right? And this convex hull is nothing but the smallest convex set that contains all points in our study, right? So this is a lot of technicality, but what I really want to emphasize here is that if the location itself is a random variable, for example, if I'm studying deforestation, and if I want to if I have a wilderness of tree canopies, and you have trees being cut at different locations in space, right? So let's say if we have tree canopies at different locations, in space, which is given already, and you want to study deforestation, and the random variable of interest is for each point that we observe a tree, structure, what is the time to deforestation, right? So what is the time at which you will observe deforestation? Then, as soon as through time, as soon as you observe a given tree being cut down, you can mark it with a circle, and that becomes a random variable of interest. So as trees are cut in space, right, you start observing a random pattern of how these point patterns are emerging or evolving through time. This specific kind of data is called as point pattern data. Let me give you some examples. So, you have, points scattered in space which you can model as different distributions, right? So, first is clustering, right? So, you see the first, box there is a highly clustered spatial data set. You have a point pattern where all the points are clustered at one location, right? So, points come together in a way that they are clustered in one location. The second is normal. So, what it means is the points have come together in space in a way that they resemble normal distribution no matter what axis they are looking at. So, if I go by this diagonal in front of your screen, you see a very, you see no data at both extreme ends of this domain. And as we move forward, you start to have a higher count of points in space. So what this, when we start to count them and plot frequency of counts, what we see is a normal distribution along these two directions, right? So you can go in any direction and you will have this pattern. Similarly, you have a random pattern where you can't really specify a distribution, and then you have a regular pattern, which is equally spaced points. Okay, so there are other examples: wheat flowering dates by location. Then you have a supercluster of galaxies. How they arrange over space. So physical scientists are very interested. They use spatial statistical tools to model locations or distribution of galaxies. So as a last item in this class, I want you to identify appropriate spatial data model for the following variables of interest. So in the first, I have a groundwater level depth given by given at 10 different locations. At all these locations, I have a x coordinate and a y coordinate. So at all given locations, I have a x coordinate and a y coordinate. I have 10 locations in all. So I will have some kind of a domain. I want to ask you what kind of spatial data model will you be able to put on it? Will it be a geostatistical data set? Will it be a lattice data set? Will it be a point patterns data set? The second example is again by district. Now we have groundwater depth by different districts in Uttar Pradesh. So these are districts in Uttar Pradesh. I want you to tell me or to think about what type of a geostatistical data set are we looking at. The third one, we want to model whether or not we observe a dry well. So what happens is that wells can go dry if groundwater levels go deep enough. And we can only, the variable of interest here is whether we have a dry well or we do not have a dry well, right? If we want to model this, what kind of a process are you going to use? So in summary, we have three different types of data variables to be modeled. We have different types of data structures in an Excel sheet, and I want you to identify which type of spatial data model which will be the most appropriate for each of these. So we'll give you some time to do that, and then we'll come back and we will resolve this query.